Welcome to today's explainer. I am absolutely pumped to have you here. So today I'm putting on my master teacher hat for the Grade 9 Science Matatag curriculum, and we're going to dive straight into one of the absolute coolest rules of the universe, Newton's third law of motion. Whether you're trying to ace your physics class or you're just naturally curious about how things work, we are going to unpack the invisible forces that govern literally how everything around us moves. Here's our roadmap for this session. We'll be starting with a rocket in space, moving on to Newton's third law, decoding the science, tackling the great force misconception, looking at forces in the real world, and finally wrapping up with why this all actually matters. Section 1, the rocket in space. Let's kick things off with a bit of a mental puzzle that's going to challenge how you think about movement. Have you ever really stopped to wonder how spacecraft actually accelerate when they're surrounded by, well, absolute nothingness? I mean, think about it. When you swim, you're pushing against water, right? When you run, you push against the ground. But out in the deep vacuum of space, there's no air, there's no ground, there's zero water. So what on Earth, or rather what in space, is a rocket actually pushing against? Picture a massive space shuttle launching into orbit. It doesn't have a road to drive on, it doesn't have air to push off of, but it somehow works. It relies entirely on this secret, mutual interaction of forces that we are about to decode. Keep this launch in the back of your mind, because by the time we wrap up this explainer, you're going to know exactly how the physics engine driving this incredible machine actually works. Moving to Section 2, Newton's third law. To solve our rocket puzzle, we've got to master the fundamental physics at play here. Okay, let's break down this masterclass definition. The law of interaction says that whenever one object applies a force on another object, that second object simultaneously applies an equal force right back, but in the opposite direction. Essentially, forces are always a two-way street. A force literally never exists in isolation, it's always an exchange. It's kind of like a cosmic handshake between two objects. So the crucial takeaway here is this. You've probably heard the classic catchphrase, for every action, there's an equal and opposite reaction. But here's the detail that trips up so many students. Actually, scratch that. It's probably the most misunderstood part of the whole law. These forces are a mutual exchange that always happens between two entirely different objects. Never just one. If object A pushes object B, well, object B pushes object A right back with the exact same amount of force. Section 3, decoding the science. Now that we've got the law down, let's build up the scientific vocabulary we need to talk about it like true physicists. We constantly throw around the terms action and reaction. So if you walk up to a wall and just give it a solid shove, your push against the wall, that is the action. But you'll immediately feel the wall resisting you, pressing right back into the palms of your hands. That is the reaction. It's the force experienced in return by the body that started the whole thing. And remember, they happen at the exact same time. Now, what's really fascinating here is how we define a system. It is super important to figure out what your system is, because an external force, meaning a force coming from outside the system, creates actual movement, like someone coming up behind you and pushing you on a swing. But an internal force, that originates from inside the system, and it does absolutely nothing to the overall motion. You know the saying about pulling yourself up by your own bootstraps? It's physically impossible. Your hands pulling and your feet being pulled are all just part of the same internal system. Section 4, the great force misconception. With those definitions locked in, let's tackle the biggest roadblock in the Grade 9 curriculum, the myth that equal and opposite forces just cancel out to zero. All right, here is the secret to mastering this whole concept. Action-reaction pairs never, ever cancel out. Why? Because they act on two completely different things. Think about it. If I push a heavy box, I'm applying force to the box. The box applies force back to me. Two different objects. Net force, on the other hand, is the sum of all forces acting on a single object. Only forces acting on the exact same object can cancel each other out to determine if that one specific thing is going to accelerate. And this setup brilliantly illustrates that exact concept. In the Matatech curriculum, we love hands-on demonstrations, and this is a total classic. Imagine a little motorized fan car. The propeller pushes air backward. That's the action. The air pushes the propeller and the car forward. That's the reaction. Boom, it moves. But now, imagine we tape a cardboard shield directly to the back of the car. The fan pushes the air, but then that air just slams right into the cardboard. Because the cardboard is attached to the car, this new pair of forces becomes completely internal to the car and cardboard system. The forces are just trapped inside. The result? The car goes absolutely nowhere. Section 5. Forces in the real world. Let's step out of the lab for a second and see how this amazing law of interaction literally propels you through your daily life. Think about something as simple as walking down the street. You probably feel like you move forward just by leaning your weight ahead, right? Well, physics tells a totally different story. When you walk, your foot is actually pushing backward against the pavement. And thanks to Newton's third law, the ground delivers an equal and opposite reaction, pushing forward on your foot. It's literally the earth pushing you forward. That's exactly why walking on smooth ice is so incredibly tricky. There's no friction for you to push back against, so the ice can't push you forward. It's the exact same deal for a vehicle cruising down the highway. A heavy truck doesn't just magically glide along. It relies on its tires forcefully gripping and pushing backward onto the asphalt. That's the action. The reaction is the road pushing those tires and the entire truck forward. You can actually test this at home right now with a balloon. If you blow up a balloon and just let it go without tying it, it zips wildly across the room. Why does it do that? The stretched rubber of the balloon aggressively pushes the air out of the opening. That's our action. And in a flawless demonstration of action and reaction, that escaping air pushes right back against the balloon, sending it flying forward. Section 6. Why this matters. So why should we care about mapping out all these invisible pushes and pulls? Is it just to pass a science test? Absolutely not. Understanding this law is quite literally a matter of life and death. Engineers use these exact principles to save lives every single day. They design tires specifically to maximize friction, guaranteeing a massive reaction force when you slam on the brakes in an emergency. They engineer seatbelts and airbags to safely manage the terrifying action-reaction forces that happen between a passenger and a car during a crash. Even the crumple zones at the front of your car are meticulously designed to absorb and redirect those extreme forces so they don't transfer into the cabin. So, bringing it all the way back to our opening puzzle, knowing everything we just talked about, interacting objects, action and reaction pairs, the balloon jet. What does a rocket actually push against to move through the vacuum of space? A car uses the road, you use the ground. But in space, there's nothing. Well, the answer is just like our balloon. The rocket engine violently forces hot expanding gas out of its thrusters. The action is pushing that gas out. The reaction? That expelled gas pushes the incredibly heavy rocket forward. It literally brings its own material into space just to push against it. How wild is that? But it leaves us with one final, mind-bending thought to chew on. If every single force in the universe creates an equal and opposite reaction, what exactly happens to the very fabric of space when two massive black holes collide? Think about that. Keep analyzing, keep asking those big questions, and I'll catch you in the next explainer.